Okay, thank you very much. So it's a pleasure to be here and to get to come and visit the Institute. And thank you very much for joining me inside when it's a beautiful sunny day outside as well. So before I get started, let me just highlight the fact that everything I'm going to be talking about today is joint with Saul Schleimer at the University of Warwick. So my plan for today is to tell you a little bit of a story about some mapping classes that we were interested in. And really, the tale is going to go along the lines of what we were really hoping for was some nice properties that these mapping classes would have. And if only they had this property, we'd be able to say some nice things about some algorithms we were interested in and things like this. And so, unfortunately, it turns out that this isn't the case. These really don't behave as nicely as we were expecting. And so today, I'm going to try and convince you of this by showing you sort of a sequence of counterexamples, each more horrific than the last. So this is what we're going to aim for. OK, so in order for me to do this, in order for us to get started, I have to set up just one little piece of notation. So throughout everything that I'm going to be doing today, I'm going to write SGP. So this is going to be the surface of genus G with P punctures. So let me just point out that there's a lot of adjectives that are missing from this definition. I'm not going to bother even to list them now, but you should be thinking about things like connected and things like this that are just going to be assumed throughout. And unlike when I give most of these talks, I'm not actually going to put any restrictions on G or P. So for example, if you'd like to think about closed surfaces, if you'd prefer not to deal with this case down here where the surface has some punctures, feel free to set P equal to 0, and everything that I say will still be true in this case. OK, so let me begin with a little caricature of one of these, and we can see some of the objects that are going on. So let me draw something like this. So here is a nice copy of the surface of genus 2 with one point punctured out of it. And what we can do is we were interested in thinking about some mapping classes on this surface, so homeomorphisms up to isotopy. So I'm going to have some map H that I want to think about, which takes things on this surface to other things on this surface. And in particular, the criteria that we're going to need some additional properties of H. And essentially what you should be thinking of is that H is sort of as generic as possible. So this mapping class H that we're going to look at, we're going to assume that this is going to be pseudo-Anosov. So this is infinite order and irreducible and really is the most generic type possible. So one of the things you can do when you have one of these mapping classes is you can apply it to stuff that you have drawn on the surface. So maybe on this surface, I've got some nice little loop gamma that's sitting here. And if I apply this this mapping class H to it, well, it goes to some other curve, which is kind of a little bit more tangled, which winds around my surface a little bit more. So up here in orange is H of gamma. And so what this is doing, this map that we're getting here, which is taking curves to other curves, or I guess more generally laminations to other laminations, is really inducing a dynamical system on this sort of space of laminations that we have sitting in the background. So let me draw another caricature over here. So over here, I have this space of all of the different laminations that I can draw. And I guess the picture here is supposed to make you think of a sphere or something like this. And this really is a sphere, just maybe not of this dimension, but that's OK. This is what my drawing skills are limited to. So this map H, which I've got on my surface, defines for me a map over here on, well, OK, this isn't just the space of measured laminations. It's actually going to turn out to be useful to projectivize this and instead look at the space of projective measured laminations. So this dynamical system over here, where you have H acting on PML, is sort of a fairly classical object and has been studied for a number of years now. I think I can say that with a reasonable amount of confidence. And in particular, perhaps the most important property that this dynamical system over here on the right has is this property called north-south dynamics. So in particular, what this tells us is that actually this dynamical system that we've got drawn over here on PML, it has a pair of fixed points. So there's the stable lamination of H, and there's the unstable lamination of H. And perhaps as the name suggests, the stable lamination is a stable fixed point. So things contract in here. And the unstable lamination is an unstable fixed point. So things repel away from here. And so if I have one of my points inside of PML, maybe there's this point here, which is gamma, and what happens when I apply this map H to it is it goes to a different point in PML, a different curve or a different lamination on my surface. So here is H of gamma. And really, from a dynamical point of view, there's nothing interesting that can happen other than the fact that things flow away from the unstable lamination, they flow around PML, and they contract in towards the stable lamination. Okay. So this is the sort of the setup that we get this nice dynamical system on PML. And in particular, the key word that I used there in talking about how these points move around is contraction. So the fact is that actually this behavior that you're sort of seeing around, let's say, the stable fixed point up here really is an honest contraction. So this picture that I've been drawing here where I have this curve gamma, and over here is H of gamma, well, maybe if I did another iteration of my map, I would have H squared of gamma, which is sitting here like this. And so what's happening is the distance from this curve that I've got, so gamma, and then H of gamma, and then H squared of gamma, every time I do one iteration, say the distance shrinks by, say, a factor of 2, something like this. So this is really nice, and this is a lovely property to have, and this is sort of a wonderful caricature for me to be able to draw for you to begin with. Unfortunately, this is rather sort of a rather nice characterization of what's actually going on the surface here. And so the theorem that I want to tell you about today is about how this idea that actually there's this contraction, and so that you're getting this sort of exponential convergence over here to the stable lamination, isn't always true. Well, it's always true you get a contraction, and so you always get this kind of exponential convergence. Unfortunately, this exponential convergence can be slow. So the theorem that I want to tell you about, so this is due to myself and Saul Schleimer. And I think in the interest of today, what I'll do is I'll state the theorem in perhaps the weakest possible way that I can. So the hypotheses will be too strong and the conclusion will be too weak, but at least this way it's perhaps a little easier to state, which is that actually, okay, so I need a hypothesis here which is going to rule out some low complexity surfaces. So if 3g minus 3 plus p is at least 4, then there are mapping classes, let's say pseudo-Anosov, mapping classes, in fact, on SGP, where this rate of convergence is, in fact, arbitrarily close to 1. So over here, where I was drawing this picture, and distances were shrinking by a factor of 2, and this was really, really good for us because it meant we were sort of going in towards this stable lamination really quickly. Well, unfortunately, this doesn't always happen. Sometimes what I can do is I can find a pseudo-Anosov mapping class where, say, for example, the distance that I see here and the distance that I see here, they differ only by 0.01%, something like this. There's a very, very weak contraction towards the stable lamination. So things can go pretty badly wrong, and in fact, they go pretty badly wrong in essentially every surface that you could possibly write down. So in order for me to try and convince you of why this is true and explain the examples that we're going to use, I need to tell you a little bit about control over this rate of convergence. And so in order for me to do this, let me start with another analogy. OK. So the analogy that I want to think about, the sort of the slightly more simplified version, rather than thinking about how these mapping classes are acting on sort of a fairly general space, is to actually begin with a slightly easier problem, which is linear transformations. So what I want to begin by thinking about, in fact, is just how matrices act. And what I'd like to say is something about the behavior of these matrices and how this rate of convergence works in this particular case. So I guess we're working over here in PML. We've got a projectivization sort of factor kicking in. So what should happen over here is I don't want to really think about matrices acting on Rn. I want to think about matrices acting on Rpn. So I'm going to have matrices, and I want to think about how they act on Rpn. So let me begin with just one particular sort of bit of setup. So I'm going to have a matrix M, and in order to make my life particularly easy, I'm going to put some assumptions on this just to help me out. So the main assumption that I want is that actually this matrix is diagonalizable over R. This is just going to help me by sort of avoiding having to keep saying assuming certain things exist and things like this. This is way too strong, and you can certainly weaken this down a little bit. So the fact that this matrix is diagonalizable over R is actually really, really useful for me because of the fact that it's going to give me a whole bunch of eigenvalues and eigenvectors. And these eigenvalues and eigenvectors are going to be really, really useful when we're thinking about these things acting on this projectivized version of this space, because of the fact that these eigenvectors that I have when we're thinking about these spaces as only being defined projectively become the fixed points that I need. So this fixed point that I see up here is supposed to sort of be reminding you of the eigenvalues and the eigenvectors that I would expect these matrices to have. So this matrix M is going to have eigenvalues lambda 1, lambda 2, up to lambda n. And associated to each one of these eigenvalues, I'm going to have an eigenvector. So lambda 1 is going to be associated to v1, lambda 2 to v2, and so on up to lambda n. And to sort of correctly characterize what's going on in the case of mapping classes, what I need to do is I need to assume a little bit about how these eigenvalues have been ordered. And in particular, I want you to order them by absolute value. So something like this. So with this assumption here that these eigenvalues are actually occurring in this order, we can try and see what happens to a particular vector when you apply one of these transformations. So let's give this a go. So if I have some vector, let's say v, well, what I can do is I can use these eigenvectors that I've got down here as a basis for my space for Rpn. So this v, I get to express it. I get to write it down as some linear combination of these eigenvectors here like this. And what I want to do is I want to take advantage of the fact that I'm working in this projectivized space to allow me to simplify my notation ever so slightly. What I'm going to do, in actual fact, is I'm going to get rid of this coefficient that's sitting right here. I can just rescale this so that this leading coefficient is 1, and that's not a problem at all. OK, so the question is, well, if this is my vector v that I've written down, what happens when I apply this matrix M? So if I apply this matrix M to this vector v, then each one of these terms that I see here just rescales by its corresponding eigenvalue. So over here, this is going to be lambda 1 v1 plus lambda 2 a2 v2 plus lambda n an vn. And again, let me try and sort of keep my notation consistent. I really don't like the fact that I've got this lambda 1 sitting at the front here, so let's get rid of that by dividing through. So this goes down here and down here. OK, so this is what happens if you do a single application of your matrix M. What happens if we do a whole bunch of these? Well, if instead of just doing a single application of this matrix M, I actually do k, I do this application k times, all of these coefficients that I see here are just going to multiply up. So in particular, because of the fact that I started with this ordering on my eigenvalues, and I guess I never really said it, but I kind of sneakily ensured that actually lambda 1 was strictly bigger than everything else. Each one of these fractions that you see here is actually strictly less than 1. So in particular, as you do more and more of these iterations, each one of these coefficients decays away exponentially quickly. So this process of applying this matrix k times means that actually this vector that you're seeing here in RPN, this converges to v1, and it converges exponentially as k goes to infinity. And in fact, I can even get a little bit of control over how quickly this convergence to v1 is actually happening. The important thing is how quickly these coefficients are decaying away, and so the important thing that I need to control if I want to get good, fast exponential convergence to v1 is I need this ratio here to be very, very small. Now, I have to do something a little bit sneaky here at this point, so let me forewarn you that it's not as bad as it seems. But really, when I started talking up here about how distances were going to shrink by a factor of 2, I used this language, and we talked about distances shrinking by some amount that's bigger than 1. So what I'm going to do is I'm going to take this opportunity to flip this fraction around. So here, what I'm going to do is I'm going to say that this converges exponentially, and in fact, the rate of convergence is lambda 1 divided by lambda 2. And I guess technically I need absolute values in here just to make it completely safe. So this process here, we get that under iteration, these vectors converge to the vector v1. And we also get good control over exactly how quickly they do it. They're converging exponentially, and the base of the exponent is like this rate here, lambda 1 divided by lambda 2. So this is how we're going to get control over this rate of convergence up here in PML, thanks to the fact that actually these mapping classes, so the mapping class group, in fact, acts on PML twice linearly. So this story that we started off with down here with matrices actually entirely holds up here for pseudo-Anosov mapping classes, so long as you're willing to go locally close to the stable lamination. All that's happening is that this mapping class is acting like one of these linear transformations in some reasonably nice coordinate system, maybe a train track coordinate system or something like this. So what we want to do if we want to get something where there's going to be really, really slow convergence, is that what we need to do is we need to build mapping classes where these matrices have this property that this quantity down here, this absolute value of lambda 1 divided by lambda 2, is very, very close to 1. Now, I need to try and get some control over this lambda 1 and this lambda 2. And so what I need to do is I need to have some kind of way of thinking about the eigenvalues associated to whatever the matrix is that's acting very, very close to this stable lamination. And so the way that I want to do this is that there's going to be so there's a matrix M which controls the effect of H near the stable lamination. And what we want to do is we want to get control over some of these eigenvalues. And in particular, I guess I'm very, very lucky that I do actually know what some of these eigenvalues are. So this top eigenvalue that I've got here, this is actually the dilatation of my pseudo-Anosov. This is this re-enlargement or stretch factor that this pseudo-Anosov applies to laminations that appear on my surface. So to control the eigenvalues of M, well, what we need to do is we need to actually control the dilatation. And so to control the eigenvalues of M, we're going to use the fact that actually this eigenvalue lambda 1, this is actually the dilatation of our pseudo-Anosov H. But I need more information than just the top eigenvalue. I need something else about the things that are lower down. So in actual fact, what's going to happen is that we're going to use not just the dilatation, but we're going to use some other Galois conjugate of the dilatation because of the fact that these things are going to be eigenvalues of my matrices as well. So this top eigenvalue is going to be just the dilatation, and this second eigenvalue, this is going to be a Galois conjugate of the dilatation. Okay. So our aim is to actually build pseudo-Anosovs where the dilatation has a Galois conjugate which is very, very close. So the aim is build mapping classes where the dilatation has a close Galois conjugate. So here, what we want is we want that this quantity lambda 1 divided by lambda 2 is very close to 1. And because of the fact that this is going to be coming up quite a lot, I'm going to give this thing a special name. So rather than having to keep on talking about the dilatation and one of its Galois conjugates, I'm going to call this thing the spectral ratio. So this is omega of H. So the ratio of these two eigenvalues. So in particular, let me just point out one thing before we move on, which is that actually this property that we're trying to drive into the ground, we're trying to make as close to 1 as possible, this is not the dilatation of our mapping class. The dilatation of our mapping class is the numerator up here. And so this process by which we'll drive this spectral ratio into the ground, this most definitely will not do anything similar to the dilatation over here. The dilatation will not be converging to 1 or anything like this. It's a very, very different property to these things. Okay, so let's see how we can actually do this. Okay. Let's go more space. Okay. So I was told that a good mathematician never does the same trick twice. And although I was later told that I misheard the word mathematician in that phrase, I think it's a good piece of advice. So I want to show you a different example to one of the ones that anyone might have seen before, or for example in the paper. So the example that I want to construct for you today is actually going to be up here on the surface of genus 2 with 1 puncture. So So let's do the construction on S21 as a nice warm-up. So I'm going to need the surface of genus 2 with 1 puncture. And to help me, what I'm going to need is I'm going to need some curves so I can do things like Dane twists and actually tell you about a mapping class. So let me get this collection of curves. So we're going to have curves A, B, C, D, E, and F. And these 6 curves are going to let me tell you about a mapping class by doing Dane twists along these things. So cut, rotate, and reglue back together. So the mapping class that I'd like to begin by thinking about is the following. So we're going to do a Dane twist. Let me put it a little bit lower. We're going to do a Dane twist along A, and we're going to follow this by an inverse Dane twist along B. So we're doing a left Dane twist on A and a right Dane twist on B. And what I'd like you to do is I'd like you to repeat this, let's say, 100 times. And then I want a similar thing to happen on the other side. So let's do a Dane twist along E and an inverse Dane twist along F, again to the power 100. So this is the mapping class that I'd like to think about. And usually this is the moment where everyone in the audience complains because of the fact that this mapping class violates one of the key things that we started off by saying, which is that this mapping class is supposed to be pseudo-Anosov. And hopefully people will agree that this mapping class is clearly not pseudo-Anosov. The dynamics that are going on over here, where we're mixing A and B, is very, very different from the dynamics over here, and very isolated from the dynamics over here, where we're mixing E and F. So this is a great observation, but there's actually a couple of other ways that you can see that this thing is not pseudo-Anosov. And one of the ways that is particularly useful in this case is to actually notice that this mapping class that I've written down here, well, it isn't pseudo-Anosov, but it still has like eigenvalues associated to it. There's still, like, I can write down invariant lamination. I can write down laminations inside of PML that are invariant under this thing. And in particular, one of the things that I can do is that there's this piece that I've got over here, which is some nice pseudo-Anosov on some subsurface or something like this. And the same thing appears over here. So actually, the pseudo-Anosov piece that I see here and the pseudo-Anosov that I see here, they have exactly the same dilatation. So this mapping class that I've written down for you here, well, in actual fact, its eigenvalues, well, I guess I know what the value is on this particular piece over here. This should have something like dilatation phi squared. So whatever this is 3 plus root 5 over 2, something like this. Well, so this piece I've got on the left-hand side, this has dilatation phi to the 200, thanks to the fact that this is multiplicative. And the same thing is true over here. So there's kind of like there's an eigenvalue that I have associated to this mapping class. And this eigenvalue is an eigenvalue of multiplicity 2. So there's something very, very weird going on here. This is not supposed to be the case for pseudo-Anosovs. Pseudo-Anosovs are supposed to have a unique maximal eigenvalue, so multiplicity 1. So what's going on here if I draw some kind of so I can draw some kind of polynomial whose roots are the eigenvalues of this particular mapping class that I've written down. Well, this does something. I don't really know what it is going to do, but all the way out here at phi to the 200, there's a repeated root. There's a root of multiplicity 2, thanks to this piece and this piece doing exactly the same thing. So our aim really is to break this symmetry. What we're going to do is we're going to take this mapping class and we're going to nudge it ever so slightly. And the nudge that I want you to do is actually going to be the following. So I'd like you to do a Dane twist along C and an inverse Dane twist along D. And the effect of this is sort of kind of nice over here. So this polynomial that I've drawn here, well, this is going to nudge ever so slightly. And maybe new roots are going to appear. That's not so much of a problem. But the key thing is that this root that I've got up here, this root of multiplicity 2, is going to separate. And if I've cooked everything up just correctly, this separation isn't going to be too much. So now this new point that I have up here, this is my dilatation. And I'm going to be very lucky that it's going to have a Galois conjugate just next to it, which is very, very close as well. So because of the fact that this number here is actually really pretty big, these things are far away, and so their ratio is very, very small, thanks to the fact that this distance is small. So this thing in orange, this is really now the minimal polynomial of the dilatation of h. So I guess maybe I should have named this h back here. So what you can actually do is, now that I've told you what mapping class to look at, you can go away and you can compute exactly what this minimal polynomial is. You can sit down and you can solve whatever the system of linear algebra is. You find the characteristic polynomial of some matrix, and you actually write down what the minimal polynomial is. So this is something that people are always a little bit skeptical of, so I will get my notes because otherwise I will make a mistake. And I guess maybe I shouldn't take all of the credit for this. I should also credit things like Sage Math, as it did a lot of the work for me. So in particular, this polynomial that I've asked you to think about here, this polynomial with these two roots that are very far away but very close together, I can tell you exactly what this polynomial is. So the minimal polynomial of the dilatation of h. This is, OK, so perhaps unsurprisingly, as we're dealing with Fibonacci numbers over here, there's going to be a whole, as we're dealing with the golden ratio over there, there's going to be a whole bunch of Fibonacci numbers over here. So this is, let's see if we can do this in one go. So this is x to the 6 plus minus 4 times the 201st Fibonacci number minus 6, x to the 5, plus 4 f201 squared plus 16 f201 plus 8 f199 plus 3 x to the 4, and then 8 times f199 squared minus 44 f199 f201 minus 8 f201. The monster that I've written down here is the minimal polynomial of this particular mapping class. And it's pure linear algebra that you need to do in order to find this characteristic polynomial. So you just need a little bit of determination or some software to help you in actually doing this calculation. Essentially, no, beyond the fact that helping you believe that this polynomial is actually irreducible. So one of the things you've got to check is actually that this polynomial doesn't factor, and that this root really is a Galois conjugate of this. And so using the fact that it's a Penner mapping class convinces you, a Penner type mapping class convinces you actually a little bit quicker that this thing is pseudo-Anosov. And so this polynomial that I've written down here really is irreducible. So there's sort of like a little leap that you get to take thanks to the fact that this is a particularly nice map.
Is the matrix from the invariant train track?
Yeah, exactly. So Penner's construction gives you the invariant train track very, very quickly. You just have to smooth out these crossings in the correct way. And the hitting matrix you can just write down straight away by writing down the individual matrices for each one of these transformations and just multiplying. And now this thing is really just the characteristic polynomial of that matrix. Are there any other questions that people have at this stage? OK, so jumping ahead slightly, all we need to do is we need to find the roots of this polynomial. So you go to whatever your favorite book is, and you start searching for how to solve degree 6 polynomials. And what you discover is that actually, in this case, you're particularly lucky. The polynomial is symmetric. You can reverse these coefficients, and that doesn't make a difference. And so this instantly lets you do one substitution and halve the degree. So you go all the way down to a cubic, and again, a cubic is particularly nice, and you can actually find the roots. So you're very happy, and you actually write down what these roots are. So there is a closed form for the for the roots of this polynomial. I am not going to write that down. It would take too long. But what I will say is that these two roots that we're interested in, well, what I can do is I can get them relatively easily from actually just looking at this polynomial. Once you go through the tricks and the substitutions, you find that actually these two roots that I've written down here, they're very, very close to this thing, and this thing is almost exactly half of this coefficient that's sitting here. There's some beautiful cancellation that occurs when you do the substitution, and it's half of this coefficient. So these roots, lambda 1 and lambda 2, they lie close to half of this coefficient, whatever it is, 2 times f201, let's say plus 3. And again, if you go through this calculation and you figure out exactly where these roots are, you can control exactly how close is. So here, where things have separated a little bit, I can actually tell you that not only are these things close, they're actually, by close, I really mean within f100 of each other. So each of these two roots that I have here, they lie within f100, the 100th Fibonacci number of this thing here, 2 times the 201st Fibonacci number plus 3. And essentially, there's nothing fancy going on here beyond actually just writing down what the roots of this polynomial is. So in particular, this spectral ratio, this omega of h, well, all I've got to do is I've got to do this division, and I know that in the worst case, what's going to happen is lambda 1 is going to be too big. So this is bounded above by I just need to overestimate things, and I need to underestimate things, and I need to do this division. And in this case, this is less than 1 plus 1 over the 100th Fibonacci number. So in particular, let me just point out one thing, which is that actually there was kind of nothing special about starting with 100 here. Perhaps you can spot the patterns that are occurring inside of this polynomial and the patterns that are appearing up here. So in particular, let me just say that this process of building omega of h, this actually converges to 1 as 100 goes to infinity. So here, if you're willing to let me make 100 bigger and bigger, this process lets me drive this spectral ratio into the ground. I can make this spectral ratio as small as you want just by picking more and more Dane twists over here. Okay. So before I talk about the more general case, I mean, here what we've done is we've done the surface of genus 2 with one puncture. I just want to make one quick remark, which is that actually this process that we've gone through here, and we've managed to bound the spectral ratio above by 1 plus 1 over some Fibonacci number like this. Well, the Fibonacci numbers are growing exponentially. So what we've actually shown is that for this family of examples, this spectral ratio here is bounded above by 1 plus, and now I'm going to write it in a slightly different form. So every time I make 100 slightly bigger, the thing that's changing over here is the word length is getting longer. So the bound that I've got above here is actually 1 plus 1 over some exponential function of the word length of h. So the amount that the spectral ratio is bounded above by 1 plus 1 over some exponential function of the word length. Well, actually, if you go and you talk to people doing things like computational number theory, they'll tell you that actually you can do, because of the fact you have good control over these polynomials, you can do the same thing in the other direction. So in the other direction, actually, you also have that the spectral ratio is bounded below by 1 plus 1 over some exponential function of the word length as well. So this is computational number theory. lets you get this lower bound. So if you want the upper bound up here, you have to go through some examples like this. Actually, this lower bound holds for all mapping classes. Anytime you have any mapping class at all, the spectral ratio is bounded below by 1 plus 1 over some exponential function. And maybe it's worth highlighting that this exponential function and this exponential function are almost certainly not the same thing. Okay. So in the remaining time, I'd like to talk a little bit more about the more general case. So here we've done genus 2 with 1 puncture, but the theorem is supposed to claim that actually this works whenever the surface is sufficiently complicated. So let's see what we can say in this case. So let me make.
So,
Yes?
geometrically, is there any significance to the second eigenvalue?
I have absolutely no idea what the second eigenvalue means. The first one I'm very, very happy with. It's the stable lamination. The second one, on the other hand, I mean, so don't forget, say, so the first one is the unique positive eigenvector. The matrix that we have is Perron-Frobenius, so it only has one eigenvector in the positive orthant. So this other eigenvector that I've got, the eigenvector associated with lambda 2 that's competing really, really hard with lambda 1, it doesn't have positive entries. So I don't know how to interpret this geometrically. It's not something that's carried by my train track or something like this. It's just something that has some negative weights on it. So unfortunately, I don't know any good way of thinking about this V2. No. The second eigenvector has negative entries.
Oh, negative entry, okay.
Yeah. Okay. Any other questions?
Are you saying entropy?
Entries.
No.
Entries. Some of the entries of some of the entries of the eigenvector are negative. Okay.
Thank you.
That's okay. Anything else? Okay. So let me produce a little table. So here's P, here's G, and 0, 1, 2, 3, 4, 5, 6. I think I need to go up to 7. Okay. So these are the different cases that we need to think about in the more general case. And so the theorem is supposed to tell us that actually we have this kind of behavior where the spectral ratio goes to 1 everywhere below this region. So everything outside of here is supposed to exhibit this kind of behavior. And I guess just now we've done the surface of genus 2 with 1 puncture. This has been taken care of. Well, so it turns out that if you want to sort of fill out the remainder of this table, you have to do some more work. You have to go through this exact same argument, this effort of writing down some polynomial and actually solving for the roots in a couple more cases. You have to do genus 1 with 4 punctures manually, and you have to do genus 0 with 7 punctures, and you have to do genus 3 with 0 punctures. But don't be afraid, it's not so terrible. We'll tell you exactly which family of mapping classes to look at, so you don't have to struggle to find one of these things like we did. And so to finish out the rest of this table, let me just tell you 3 facts that help. Okay. So let's begin with some facts. So let me just say these things in order, and we'll see how these actually fill out the rest of the table. So the first thing that I want to use is the fact that actually, because of the fact that periodic points are dense on surfaces for pseudo-Anosovs, in fact, what I can do is if I have one of these examples where I have this exponentially converging, this family where the spectral ratio is converging to 1 exponentially, in fact, what I can do is I can put in an extra puncture without causing too much problem. So I can produce an additional periodic point. I crank everything to a high enough power so it's actually a fixed point, and then I'm good to go. So the first fact is that actually, so I'm going to write that if S is in exp. So this is going to be the set of surfaces with such a family. Then, sorry, I should have actually put this in. If SGP is in here, then in fact SGP plus 1 is in exp as well. And this is very handy because of the fact that this has already filled out all of these rows off to the right. Okay. So if we're going to fill out the rest of the table, we better do something of higher genus. And so the second fact is that actually this property is reasonably well behaved under taking covers. So the second fact that I need is that if, let's write it this way, so if S covers S prime, which is in exp, then in fact what I can do is I can take my converging family that I have down here, crank it to a high enough power so that I can actually lift all of these things, and then lift this family up to S as well. And that will give me an exponentially converging family up here. So anytime I can take a cover, this actually lets me put another one of these surfaces into this set X. So this lets me fill out a few more of my entries. Let's see, what do I get for this for free? Well, somewhere down here, I have the surface with odd genus. So down here, so this is G odd, some odd genus surface. Well, this thing that I've got down here is a cover of S30. So the fact that this thing has been done and has been taken care of does this case as well, and so we get the entirety of this row for free as well. And unfortunately, a similar thing isn't quite true in the even case, but there's something close. So if G is even, well, we can't do any kind of. It turns out you can't do any kind of like covering up to here back to one of these cases necessarily. But there's a sort of a nice branched cover, which becomes a reasonable cover if you let me put in a few punctures. So actually, the thing that I want to think about is SG. Let's try and line it up. SG2. So this is SG2, and this thing down here is actually a cover of S22 up here. And so again, this fact tells you that actually this case is okay as well. So this is a cover up here, this is a cover up here, and so again, everything to the right of this thing here is okay. Everything works. So we're almost done. We've almost filled out the remainder of this table, but there's a couple of little cases floating around that I want to point out, which is taken care of by this third fact, which is that actually if S is in X, and let's name this properly, SGP is in X, and there's a singularity, or there is a puncture with order bigger than 1 for every mapping class in my family. So anytime I look at this puncture, I look at the stable lamination, I see at least 2 prongs coming out of this. Well, then what I can do is I can fill in that puncture, and whatever the stable lamination is, it'll survive under that filling. So in fact, so long as I have a puncture whose order of the singularity is at least 1, then what I can do is I can do this filling, and this will actually this family will actually survive. So then SGP minus 1 is in X. And here we're very fortunate that what we did was we built this family here by taking a cover. And in fact, we did this cover by unwinding about the punctures. So whatever the order of the singularities are here, well, it's at least the degree of the cover times by the order of the singularities here. And we took at least a degree 2 cover or something like this, so the order of the singularities down here are all good. So this third fact lets you actually do these 2 steps back and fill out the remainder of this table. Okay. So these are the 3 things that you need to know if you want to be able to do all of these surfaces, not just these 4 examples that we will tell you how to do. So in the remaining 10 minutes or so, I'd like to tell you a little bit about what is going on up here in this region back here. So there's certain things that I guess I should say straight away where this problem is not interesting. So I guess any one of these 4 cases up here isn't really worth thinking about due to the fact that there are actually no pseudo-Anosovs that you can write down on any of these surfaces. So you shouldn't bother trying to think about these things. It's not a reasonable place. There's also something a little bit different in these lower complexity surfaces here. So let's use a color. So there's this one here, and then there's these 2 here. So in these surfaces, so in the 4 times punctured sphere, the torus, and the once punctured torus, actually the dilatation is a quadratic irrational. So it only has one other Galois conjugate. It's reciprocal. So what I'm going to try and do is I've got to try and squeeze this dilatation and its reciprocal to be as close as possible. And what's going to happen is I'm going to try and pull the dilatation down, and the reciprocal is going to go up. And unfortunately, because of the fact that dilatation is bounded away from 1, what's going to happen is I'm going to get stuck. I'm going to try and pull these things together, and unfortunately, the dilatation can't go down arbitrarily close to 1, so that its reciprocal can't come arbitrarily close to 1 either. So these things remain a bounded distance apart. There's a minimal spectral ratio in this case. In this case, you do not have this property that spectral ratio becomes arbitrarily close to 1. Here, the spectral ratio is actually bounded away from 1. So unfortunately, you can't squeeze these things together as much as you like. There's a definite gap and a definite amount of spectral ratio. So the final cases that are sort of worth thinking about are these low complexity surfaces. Here. So let me just see if I can make this thing work. So I press this, and then I press this, and hopefully everything comes up. Oh, thank you. Thanks. So this is one of the really low complexity examples. This is the twice punctured torus. And again, here I've drawn a little collection of curves A, B, C on it. So we actually have a generating set for the pure mapping class group, but whatever. So this is actually the example that we started by thinking about. This is the first place that we went to, the first thing where there's the possibility that actually this spectral ratio can become arbitrarily bad. And really sort of the way that we sort of went about this, and maybe this is a really good advertisement for sort of maths by computer or something like this, is brute force computer experimentation. So it turns out that actually the amount of code that you need in order to be able to get these examples to work is fairly minimal. There's this nice library called Flipper that I wrote, which takes care of most of the work for you. But essentially, all you need to do is load in one of these examples, and you can just work through all of the mapping classes of a particular length. You can build the mapping class. If it's pseudo-Anosov, you can find its roots. You can sort these, and then you can print out this absolute value of this ratio. And I guess this is Python, so it's 0 index rather than 1. But I think we can handle this difference here. So with such like a low barrier to entry, it seemed like a shame not to do this. And this was our sort of first set of computations that we actually did. So if you do this, you can build a little table like this where you write down all of the words and you compute their corresponding spectral ratios. And perhaps this isn't so interesting until I take this table and actually sort it by spectral ratio. So these are all of the. This is the guy with smallest spectral ratio, then the next smallest, then the next smallest, and the next smallest, and they're slowly becoming bigger and bigger and bigger. And in fact, maybe it's not too hard of a leap to guess at what the right thing to predict should be. And this is actually the first proposition that we proved. So the first case, which is that actually if you do this mapping class, so you do a Dane twist along A, K Dane twist along B, and then an inverse Dane twist along C. Well, okay, modulo this fact that you can't take 2k plus 1 to be a square. Actually, this spectral ratio is bounded above by 1 plus 5 divided by the square root of k. So here, even in this example, even in this case, you still get that the spectral ratio goes to 1. you can make the spectral ratio arbitrarily close to 1, and you can make this rate of convergence arbitrarily slowly. But it seems a little bit different. Really, in this low complexity world, this remark that I made over here isn't true. You still have this lower bound, which is 1 plus 1 over an exponential function of the word length. But now over here on the other side, instead of 1 plus 1 over an exponential function, it's 1 plus 1 over a polynomial function. So here in these example, in these whatever it is, 5 cases that I left out, the cases where 3g minus 3 plus p is at least 2, you still have convergence to 1. The spectral ratio still becomes arbitrarily close to 1. It's just that the behavior is very, very different. We can only find these examples where, in fact, the spectral ratio is going to 1 polynomially with the word length. And so, really, the theorem that I started off with, I could have made it stronger in 2 different ways. I could have either stated that actually, if so long as the complexity is at least 2, you get to go to 1. You get to become arbitrarily close to 1. Or if the complexity is at least 4, then you get to go to 1. You get to go arbitrarily close to 1, and you go to it exponentially quickly with the word length. You get to exhibit this worst possible behavior with the spectral ratio. You can't do any worse than this exponential behavior. So this is sort of a very sort of puzzling thing, and we're still trying to figure out which side of this inequality to make stronger. Whether we should be looking for another family where, in fact, the spectral ratio goes to 1 exponentially, or whether we should try and crank up this lower bound. And maybe it's worth pointing out that actually all of this sort of experimental type data seems to be indicating the fact that actually the place to make the correction is in the lower bound. In these low complexity surfaces, you should expect the spectral ratio to be bounded below by 1 plus 1 over a polynomial function if you believe some of this data. Okay.
So were A and C the 2 that didn't intersect? Sorry, I forgot what picture.
Yeah. So let me go back. Yeah. A. So the chain is A, then B, then C. So actually, where has it gone? So this is the particularly nice way of writing this mapping class. I think if you square it, then actually one of the things that drops out is that, so because of the fact that B is taken off of itself by A C inverse, you actually get that what's going on, if you look at the square rather than looking at this particular mapping class, you have a pair of annuli. And what you're doing is you're doing a huge number of Dane twists along those annuli, and then you're doing a little bit of mixing in between the 2 of them. So it's very, very similar behavior to what we were doing in the surface of genus 2, where we had a pair of identical subsurfaces. We did a huge power of some mapping class on them, and then we blended things together just a little bit, just to make sure we really were pseudo-Anosov. So here, what's going on really is that our surface isn't big enough to contain a pair of interesting surfaces where we can do something pseudo-Anosov. So we're forced to use annuli. And this is the only stuff that we can fit in, and so the spectral ratio here is growing like 1 plus 1 over a polynomial function rather than 1 plus 1 over an exponential function. So this is very, very different behavior. Okay. So I have 1 minute remaining, so maybe I can put up one last slide just to say one final thing and finish, which is that actually this process that we went through, where I told you what mapping class to look at, say for example in this case back up here, well, it turns out, or one of the things that it turns out that you can try and do when you have access to stuff like this is that you can try and do sort of things like random experiments over here. You can see like just how hard it was to actually stumble across this particular mapping class, which has this really nice property. So the final slide that I want to put up is this one here, where what we did was we did a very similar thing, but for the 7 times punctured sphere. So one of these example surfaces where we can get the spectral ratio to go to 1 exponentially with the word length. And so what we did was, well, let's just pick some samples at random and let's see what's actually happening. And so the point is that this sort of behavior, or the generic behavior that you see up here, that actually these mapping classes, well, their spectral ratio is actually growing exponentially. It's a logarithmic scale on the y-axis. And so for a typical kind of thing that you would pick of, like, maybe length 200 or something like this, the spectral ratio is pretty decent. Things are contracting by a really strong factor. Whereas these examples that we're talking about over here, they all sort of live right down here, right on the line y equals 1. So these examples that I've been showing to you today, they're very, very atypical if this experiment is telling you anything. So these examples sort of seem very pathological, and unfortunately this construction that we've gone through over here is actually extremely sensitive to any kind of perturbation. If you try anything here other than the Dane twist about C and the Dane twist about D inverse, and you manage to get the spectral ratio to go to 1 exponentially with the word length, please tell me. We can't find anything else other than something like this, or conjugate to this, or something like this. Okay, but I think this is a good place to stop. So thank you.